Assalamu alaikum, you all. I hope you all are fine. Welcome to the chapter of transition and inner transition elements. I'm your teacher Sumayya Khan, and we have completed quite a good part of this chapter in our previous lectures. Today, students, we are going to discuss about the electronic configuration of lanthanoids first. The general electronic configuration for all the 14 lanthanoid elements can be given as xenon 54 to 4f 1 to 14 electrons, then 5d may have 0 to 1 electron, and 6s will have 2 electron for all the 14 lanthanoids. Okay, depending on the lanthanoid under discussion, the number of electrons will vary in the 5d and 4f orbital. In all the 4f in all the 14 lanthanoids, the electrons till 56 electronic configuration till 56 electron will be same. For 54 till 54 electron, it would be similar to the noble gas xenon. Then the next 2 electron will enter into the 6s outer 6s2 orbital. Okay, and then as the atomic number increases from 58 to 71, the next electrons will go into either f orbital or d orbital. Okay, all of these will contain electrons in their f shell. That is why they are called as f block element. Okay, now instead of writing the long electronic configuration for such a big atomic number, we make use of the noble gases, which comes just before our atom under the or element under the study. For example, if we are doing the study on cerium, the atomic number of cerium is 58. So we know that electronic configuration for cerium can be cut short as xenon 54, then 6s2, that is 56. Then the next 2 electrons will go into the 4f orbital. Okay, so this is the general electronic configuration. For your reference, the electronic configuration of xenon is also mentioned at the bottom. You can write this electronic configuration of xenon also with the help of the Aufbau law. Now here I have given the mnemonics for memorizing the lanthanoids. Okay, so Selena Prasad नहीं, पैम एंड सैम यूरोप गए तो डायरिया हो गया, अरे तुम यहाँ भी लूसी. So Selena का CE, Prasad का PR, all the alphabets that are written in the blue are one of the lanthanoid element, and these words are arranged in such a way that will give you what? The lanthanoid series in the order. So C is for cerium, Prasad ka PR is for praseodymium, then comes nahi ka N, but here D is not written, that you have to memorize that it is ND representing neodymium. Then from PAM you should take PM for promethium. From SAM you will take SM for samarium. From Europe you will take ER for europium. गए से आप लेंगे G and you will add small d, GD, to represent gadolinium. 2 से आएगा आपका T और साथ में आप लगाएंगे small b to represent the element terbium 65. उसके बाद आ रहा है डायरिया. डायरिया में you will add Y, dy for representing the element dysprosium. हो गया का होलियम HO, अर के लिए ER for erbium. तुम से you will take TM for making thulium. यहाँ भी से you will take YB for mentioning ytterbium, and in the end we have Lucy, where you will take LU and it will be called as lutetium. Okay, there are many other mnemonics. You can go through the net, you can search the net, and whichever you find easy you can memorize it. Okay, एक और हम लोगों ने किया था स्कूल में अपने कॉलेज में, that was लेके, that started with the lanthanum. लेके सर पे नया पैजामा सैम यूरोप गया था. फिर उसके बाद ये जो डायस्प्रोसियम से हम लोगों ने खुद से बनाया था, दी हो अरे तुम यहाँ भी लूसी. ओके, so whatever you find easy, you can choose that, and you should memorize the lanthanoid series. Okay, one more is here in English. Last century presented new democratic prime ministers on social media. Okay, it's almost half of your lanthanoid elements are here. Okay, then European government decided to ban dirty hotels entirely to make yellow buildings luxurious. Okay, so here also the symbols for each of the lanthanoid element in the series are mentioned, so you can memorize these mnemonics to memorize the lanthanoid series. Okay, now let's go back to the this thing of Bohr principle. How do we fill the electrons successively into the suitable shells? Okay, so by making use of the Aufbau principle, you can always write the electronic configuration of any element. If you memorize the mnemonics and you remember that the elements of the lanthanoid starts with 58 and ends to 71, you can write its electronic configuration easily with the help of this Aufbau principle. So we know that from 1s, 2s, 2p, 3s till 5p, we are actually till 6x orbital, that is the first, second, third, fourth, fifth, and the sixth arrow. Look at the arrows from above till the sixth arrow. Till the sixth arrow, you have the electronic configuration for 56 electron, okay, which is equivalent to the electronic configuration of element barium. After that, students, you can see that we have to fill 4f orbital. After 6s orbital, which orbital should be filled? 4f orbital. And then there is 5d orbital. But in lanthanoid, you will find some irregularities in the filling of these electron into the particular orbital, and in some of the element you will find that the 5d orbital is also filled. Okay, even though there is a space in the 4f orbital, for available space is there in the 4f orbital for filling that electron, but still the electron goes into the empty 5d orbital. Okay, lanthanum में क्या होता है? Lanthanum is not an f block element. Why? Because in lanthanum the electron, the 57th electron, goes into 5d orbital instead of going into 4f orbital. According to Aufbau, उसको 4f में जाना चाहिए था, लेकिन it went into 5d. Okay, that is why it is kept under the d block element. Okay, so after lanthanum you will find that every element that is from cerium to lutetium, you are going to find an electron in the 4f orbital. Okay, now look at the electronic configuration of these elements: observed electronic configuration as well as expected electronic configuration. So let's start with cerium. Okay, the atomic number of cerium is 58. The expected electronic configuration was, according to Aufbau principle, was 6s2 and then 4f2. Okay, what we are doing, we are going according to Aufbau principle. But what is observed here, instead of moving into the 4f orbital only, one of the electron is in the 5d orbital, as it was in case of lanthanum. Okay, then again let's move down to praseodymium. In praseodymium we have 59 electron, so 56 tak is same as Xc 6s2. Then 3 more electrons are there, so what we expect, these 3 should go in 4f orbital. This is what is expected, and this is what is observed also. Okay, in the same way, for neodymium and for promethium, as well as for samarium and europium, the expected and the observed electronic configurations are same. So only cerium does not show what? Expected electronic configuration. But after cerium, from praseodymium to europium, we observe that expected and observed ground state electronic configurations are same. Okay. Now look into the gadolinium. Gadolinium 64. We have expected that xenon 54, then 6s2, that is 56 electron. When you minus 56 from 64, you are left with 8 electrons. Okay. So according to Aufbau, we expect that these 8 electrons should go into 4f orbital. But what we observe that instead of showing 4f8 configuration, the observed configuration is 4f7 and 5d1. One of the electron goes to 5d orbital. And the reason for this is assumed to be that when the when the element have 4f7 configuration, the f orbital is exactly half filled. And we know that empty, half filled and completely filled orbitals gives extra stability to the atom. Okay, so to acquire that extra stability due to the half filled configuration of 4f orbital, one of the electron jumps into 5d orbital and we have 4f7 electron in case of gadolinium. Then after gadolinium, from terbium to lutetium till the last lanthanoid, the expected and observed electronic configurations are same. Okay, so only one variation is observed from the expected configuration, which is in case of gadolinium, where the one of the electron which is expected to be go into the 4f orbital, so that the electronic configuration could be 4-8, is not that, but we have the 4f7 5d1 configuration, and that is to acquire what? To acquire the extra stability for the exactly half filled f orbitals. Okay, we know that exactly half filled orbitals gives extra stability to the atoms. Okay, so to achieve that extra stability, one of the electron goes into the 5d orbital. Okay, now this is the valence shell electronic configuration of lanthanoids, which can be represented by the given formula, where n is your outermost principal shell, then n minus 1 d orbital may contain 0 to 1 electron, n minus 2 f orbital may contain 1 to 14 electron. Okay, so as in case of lanthanoids, your n, your principal shell is 6, then n minus 1 is 5 and n minus 2 is 4f orbital. Okay. Now lanthanum, gadolinium and lutetium possess single electron in 5d subshell to keep 4f orbitals empty, half filled and completely filled respectively. Now lanthanum is also mentioned along with the lanthanoids. So sometime you will find that lanthanum is mentioned with the lanthanoids, sometime it is not. But actually lanthanum is a part of D or D block. Okay. So if you are not mentioning lanthanum, you are not doing wrong. Now let's see why do they have one or electron in their D subshell. But the expected configuration was what? That electron should have been present in the 4f subshell according to the Aufbau method. Okay. Now when they have this one electron, when this one electron jumps into 5d subshell, these orbitals will get what? F0 configuration, F7 configuration and F14 configuration. These electronic configurations achieve extra stability due to the empty, half-filled and completely filled orbitals. Okay. So to attain that extra stability, to achieve that extra stability, what happens? These atoms give what? A variation from the expected electronic configuration. In the observed configuration, we have discussed that. Okay. Now, oxidation states of lanthanoids. Remember, students, all lanthanoids will exhibit +3 oxidation state. Okay. Apart from +3 oxidation state, few of the lanthanoids will also exhibit some other oxidation state. For example, cerium and terbium exhibit +4 oxidation state. +4 means loss of 4. They are stable by losing 4 electrons. Now look at their general electronic configuration first. Electronic configuration of cerium is given as xenon 4f2 5d0 6s2. Now if cerium loses 4 electron, the electrons will go from 6s orbital and 4f orbital. Okay. So when the cerium does that, it will have empty 6s orbital and it will have empty 4f orbital also. Okay. So they are going to have the empty orbitals in the +4 oxidation state. That is why they will form a stable what? Ion or a compound, whatever they are going to form in plus, they will be stable in +4 oxidation state. Okay. In the same way for terbium, look at the electronic configuration of terbium. It has 4f9 5d0 6s2 electrons. So when it loses 4 electron, the 2 electron goes from 6s and 2 electron goes from 4f9. So your configuration now becomes 4f7 5d0 6s0. Okay. 4f7 is what? Exactly half filled f orbital. So it will achieve some extra stability. That is why terbium in +4 oxidation state is stable and it can exhibit +4 oxidation state also. Okay. Now, europium and ytterbium exhibits +2 oxidation state. Now, if you know how to correctly write the electronic configuration of these elements, and if you have remembered that this is the atomic number of this particular element, you can easily understand why it is stable in +2 oxidation state also. You can see europium have electronic configuration 4f7 6s2 and ytterbium have 4f14 and 6s2. So by losing the 2 electrons from the outer 6s shell, they will acquire the +2 oxidation state. Okay. And europium will have 4f7 configuration, which is exactly half filled, and ytterbium will have 4f14 configuration, which is a completely filled state of f orbital. So they will achieve extra stability by having exactly half filled and completely filled f orbitals. Okay. So that's why europium and ytterbium form stable +2 oxidation state. Okay. The reason is given above, because they will have 4f7 and 4f14 configuration, which provides its extra stability. Now comes another important topic, color and spectra. Now some trivalent, look, when you look at the lanthanoids generally, all lanthanoids are silvery white in their atomic neutral state. Elemental state mein these are what? Silvery white metals. Okay. But in their oxidation states, some of them are colored. Some trivalent ions of lanthanoids are colored in solid state as well as in solution. Now the color of lanthanoid ion is due to the FF transition. Like we have studied the DD transition, there is also FF transition, which corresponds to the energy in visible region of electromagnetic spectrum. That is, our visible light contain enough energy which can be absorbed by these electrons which are present in f orbital, and they may go under FF transition of electron, emitting certain radiation of particular wavelength that will be responsible for the color of that particular ion or compound. The colors of ions having NF electron is about the same as those having 14 minus F electron, where N is an integer from 1 to 13. What is mean by this now? Now suppose there is an atom lengthenoid with NF electron. Suppose in F orbital it has 2 electrons. Okay, so we'll say NF electrons. If F orbital contains electrons, it will have particular color X. Okay, and there is one atom in which if you minus that 2 from F, how many electrons you will have? 14 minus N, you will have 12 electrons. Okay, so if there is a lanthanoid with 12 electron, that is 14 minus N, okay, will also have the color X. Okay, so N number of electron as well as 14 minus N electron will have almost same color. Okay, let's see some examples. Promethium ion. Promethium, all are lanthanoids ion. Promethium plus 3 ions. The number of electrons left in F orbital in case of promethium is 4f2. So your N here is 2. Okay. And the color of promethium is what? Green. In the same way, if you had 12 electrons also, then also you will have what? Green color. For example, in thulium plus 3 ion, Tm plus 3 ion, we have 4f12 electrons. Okay, the color of the ion is green. Now here N is 12. Okay, again the color is what? Green. You compare the example of promethium and thulium, where the value of N and 14 minus N are different, but the color of the compound is same. In the same way, neodymium and erbium also will exhibit the same behavior. In case of neodymium plus 3, the value of N is what? 3. And the color of our neodymium compound plus 3 compound is pink. In case of erbium, we have value of N equals to 11 and the color of the compound is pink. Now let's look at in the 14 minus N way. When you do the 14 minus N formula in neodymium, you will get 11 electrons in F orbital. And when you do the 14 minus F electron, 14 minus N electron in erbium plus 3, you will get 3 electrons. Okay, so N, if NF electron is equivalent to 14 minus N value, then you will have what? The same colored compound for different lanthanoid element ion. Understood? Now it is a very important topic, lanthanoid contraction. Now what is mean by lanthanoid contraction? As we move along the lanthanoid series from cerium to lutetium, there is a decrease in atomic and ionic radii. This decrease in the atomic and ionic radii is called lanthanoid contraction. Okay. Now this decrease in atomic and ionic radii is quite small and is less than the expected values. Okay. So this decrease is quite steady, gradual and small. Okay. Now why this is happening? The reason for lanthanoid contraction is one of the reason. Two main reasons are there. As we move from one element to another in any series, not only lanthanoid, in any series, the atomic number increases by 1. Okay. And when the atomic number increases by 1, the nuclear charge also increases by the 1 unit, because 1 electron is being added to that atom we are going to. Okay. The new electrons are added to the same inner 4f subshell. In case of lanthanides, whenever we are moving from one element of lanthanoid to another, one more electrons are being added to the 4f subshell, which is quite inside the outer of the outer 6s orbital. Okay. However, the 4f electrons shield each other from the nuclear charge quite poorly because of the very diffuse shape of the f orbital. We should remember that f orbital have a diffuse shape, because of which the electrons which are present in f orbital will not shield each other from their effect of nuclear charge, from the effect of nuclear charge, or from the effect of outer environment, because of the poor diffuse shape of your f orbital. The nuclear charge however increases by 1 at each step. Each step में एक एक न्यूक्लियर चार्ज बढ़ता जा रहा है, जैसे जैसे एक इलेक्ट्रॉन बढ़ रहा है, ठीक है, लेकिन उसकी क्या हो रही है, एक दूसरे की शील्डिंग नहीं हो रही है. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron also increases. Now, suppose initially the 4f orbital had only one electron. Okay, the effective nuclear charge experienced by it was something else. Now that the same electron is going to experience quite a high effective nuclear charge when 7 more electrons or 4 more electrons are added to the same subshell, because they are present at the same position. The effective nuclear charge experienced by each of the electrons that are present in the f orbital will be same as the atomic number goes on increasing. Okay, because the pull in the nucleus is increasing. Suppose अब क्या हो रहा है कि सपोज यहाँ दो टीम थी, पहले ये दोनों टीम में एक एक खिलाड़ी थे एंड यू वर प्लेइंग टग ऑफ वॉर, ठीक है. अब क्या हो रही है, सामने वाली टीम में खिलाड़ी बढ़ते जा रहे हैं, एक ताकतवर खिलाड़ी बढ़ता जा रहा है, और आपकी टीम में कमज़ोर खिलाड़ी बढ़ता जा रहा है. ताकतवर खिलाड़ी तब कमज़ोर खिलाड़ी बढ़ता जा रहा है हर टीम में हर बार, समझे. लेकिन वो जो कमज़ोर खिलाड़ी है वो सारे के सारे मिल के भी इन ताकतवर खिलाड़ी लोग को नहीं हरा पाएंगे, ठीक है. तो यही चीज़ हो रही है, इफेक्टिव न्यूक्लियर चार्ज इंक्रीज हो रहा है, नंबर ऑफ इलेक्ट्रॉन्स भी इंक्रीज हो रहा है, लेकिन नंबर ऑफ इलेक्ट्रॉन्स आर नॉट shielding each other, and they are poorly shielded, and they are experiencing more effective nuclear charge. Okay, as a result the whole 4f electron shell contracts. वो सारे के सारे खींच के क्या हो जाते, छोटे हो जाते, करीब आ जाते न्यूक्लियस के. As a result, the whole 4f electron shell contracts at each successive element. This results in gradual decrease in size of lanthanide with increase in atomic number. Okay, तो क्या हो रहा है यहाँ पे, आपकी साइज ऑफ लैंथेनॉइड कम होती जा रही है, एटॉमिक नंबर जैसे जैसे बढ़ता जा रहा है. जनरली हमेशा क्या होता था, हम लोग देखते थे आउटर मोस्ट शेल में इलेक्ट्रॉन्स जाते थे. जब आउटर मोस्ट शेल में इलेक्ट्रॉन्स जाते हैं तो जो अंदर वाले जो ऑर्बिटल्स और शेल्स होते हैं वो लोग शील्ड कर देते हैं आगे वाले वैलेंस इलेक्ट्रॉन को न्यूक्लियर इफेक्टिव न्यूक्लियर चार्ज से. लेकिन इन केस ऑफ लैंथेनाइड क्या हो रहा है, आपका जो शेल हो रहा है, आखिरी शेल इलेक्ट्रॉन्स है जो, वो आउटर मोस्ट शेल में नहीं जा रहे बल्कि काफ़ी अंदर मौजूद 4f ऑर्बिटल में जा रहे हैं, विच इज़ क्वाइट इनसाइड. Above 4f there is 5 and 6 or sub principal shell. Okay, तो ये 4f is quite inside. तो ये क्या हो रहा है, ये शील्ड नहीं हो रहा है, या ये शील्ड हो रहा है आउटर वालों से, और ना ये शील्ड हो रहा है अपने ही इलेक्ट्रॉन से, बिकॉज ऑफ इट्स पुअर डिफ्यूज्ड शेप. ओके, so that is why what happens with the addition of the electron when we move from lanthanoid into the series, the addition of each electron causes increase in effective nuclear charge and contraction in the size of the lanthanoid element. This gradual decrease is known as lanthanoid contraction. You just read it 2-3 times more, you will understand it better. Now here you have shown that how lanthanoid or how the size of radii decreases from lanthanum to lutetium. Okay, so you can see here that ionic radius of lanthanoid ions are given from 104 approximately to 85. तो 20 का ही डिफरेंस आया है, देखो 20 पिकोमीटर्स का ही डिफरेंस आ रहा है. तो इतने सारे एलिमेंट्स, 14 एलिमेंट्स, 15 एलिमेंट्स यू आर considering, but the size decreases so less due to what? This decrease is the, look how gradual decrease they are showing. Okay, this decrease in gradual decrease in size is known as what? Lengthenoid contraction. So students, let's finish our lecture today here only. Inshallah, we'll meet in the next lecture. Until then, please be safe. Take care of yourself. Do study at home. Allah Hafiz.